dear friends, now we will go for your the different conditions. So, what about the change in entropy when there is an ideal gas or the perfect gas which is undergoing to the change in process? So, we will consider change in entropy for an ideal gas. So last lecture we considered there is a concept of the entropy in the entropy changes in a reversible process and irreversible process. Now we consider if the system is an your ideal gas, then what about the entropy? Now here entropy is the state property. It can be really only deduced by the carefully experiment. If you want to prove this entropy is the state property for a special and important case of an ideal gas which is undergoing to the reversible process. To make the process reversible, should be remember here ideal gas, but there is a reversible process. Reversible process. Okay. So to make the reversible process, we should be remember if you want to any process or any changes take place in a thermodynamic and it is in reversible, that is first condition for reversible. Whatever your changes is take place, that changes must be very slowly. It can be say it is a slowly step by step. Okay. So what happens when ideal gas goes from the changes so slowly, each and every time there is an equilibrium state is an present. Equilibrium state will be the what happens? There is no exchange. So for each small state, amount of heat transfer to the system are taken outside the system. Okay. Now suppose in this case dq is the small amount of heat absorbed or rejected. Absorbed or rejected by your system. System, that is your ideal gas. Due to this, there is a change in internal energy. There is a change in internal energy. Should be remember when you have to apply the amount of heat to that system, so there is a change in internal energy, and there is a work done. Now this work done, two type of work done. Work done by the system or on the system. On the system. So this is related to the first law of the thermodynamics. First law, and that first law is the dq is equal to du plus dt. If the change in the volume is dV, then you should be written here pdv. Du is a change in internal energy. So for 1 mole of the gas, du is equal to Cv into dt. So it can be written here dq is equal to Cv dt plus P into dt. Now this is your idea, first law of thermodynamics. If you have to divide by the t throughout the equation, if you divide by t, then we got dq upon t is equal to cv dt upon t plus p upon t into dt. If you divide by the t, so we got this. Once again, if you have to use the ideal, this is the ideal gas. So for ideal gas, Cv is equal to R. Here is the dV, here is the P. So can we change replace this P by the another parameter, P is equal to RT by D. So you have to put this here. So we got dq upon d is equal to Cv into dt upon t plus RT upon V into T. So Tt will be cancelled. So remaining term is the here. This Tt will be cancelled. So we got Cv dt upon T plus R upon V into T. Now suppose your system is going to be changed from the initial state I to the final state F. Okay? And we know there is a dS is equal to dq upon T. This is a change in entropy. Should we remember that the two adiabatic curves, it is very close to each other. The small amount of heat is dq, T is the temperature. So change in entropy is the dS is equal to dq upon dt. So we can be written here dS is equal to Cv dt upon T plus R dV upon V. So if a system changes from initial state to the final state, and if you consider the total change in entropy, you want the total change, in entropy. So we take the integration of the above equation. So we got the integration ds from I to the F is equal to Cv is the constant. Take the integration from I to the F dt upon T plus R is gas constant, take outside. So from the integration from I to the F, so we got the dV upon V. Now suppose yes I, F is integration limit, integration of the ds is yes, Cv, integration of the 1 upon T is I into F plus R log V from I to the F. Now it should be 1 upon x integration is a log x. So we got SF minus SI is equal to CV log TF minus log TI plus R log VF minus log CI. So we got the equation CV log TF upon TI plus R log CF upon VR. Now this is an equation for change in entropy It may be given by the delta H symbol also. Anyway, should be remember here. Change in entropy for the ideal gas if it is in a reversible. So entropy changes we did not have to specify particular reversible process when you integrate which is not for the reversible process. The change in entropy between the only two states, initial and final state, we do not consider as a reversible. So it depends upon only the two states. It is called as a entropy is a state function. It depends upon initial and a final state. That is, it is in between the two equilibrium state of the system. Now we consider there is a change in entropy when gas expand under isothermal condition. So it should be remember isothermal condition. Now you want to determine the change in entropy, but which condition there? Expansion, but there is an isothermal expansion. Condition is an isothermal, means temperature is a constant here. So suppose there is an ideal gas which is expanded isothermally, then there is an isothermal change in occurs, so temperature remains constant, so there is no change in the temperature, so dt is equal to 0. If the dt is 0, should be remembered for ideal gas there is a free from the intermolecular force of attraction, so change in internal energy, that is internal energy is a function of the T. It depends upon the temperature. So change in internal energy is 0. Why the change in internal energy is 0? Because the ideal gas we consider here, and there is an isothermal process. If there is isothermal, temperature remains constant. So change in the temperature is 0. Ideal gas is there. Intermolecular force of attraction is absent. So internal energy depends upon the only temperature. So we got the first law of the thermodynamics. Now the first law of the thermodynamics. So first law of thermodynamics is dq is equal to du plus tdv. Now du is equal to 0. So we got the dq is equal to tdv. dq is equal to c. So by the second law of the thermodynamics second law is it should be remembered, this is the equation for second law of thermodynamics. ds is equal to dq upon ds that is the average consider I and x. So we got the dq upon c. Okay. Now it should use this equation. It should be use that equation here. So this equation becomes integration from 1 to 2 P upon T into D. Now can use order of equation P is equal to R. So P is equal to RT upon P is equal to RT upon. You have to put. It should be put now. Here. So we got integration from 1 to 2 RT upon V into P into V. So we got integration from 1 R upon V into V. R is the gas pointed outside, that is 1 to the 2, that is 1 upon V into V. So integration of the 1 upon V is the log V. So we got R into log C2 minus log C1, and this equation is written as R into log C2 upon V1. Equation for the change in entropy. It may be written as a delta S or S2 minus S1. Change in entropy during the iso and of an ideal gas. Well, that is a thermodynamics variable. We can use this. That we have already studied the change in entropy S minus SI is equal to R into log VF upon V log CF upon for ideal gas. Now there is a S1, it can be changing otherwise as like. So it depends upon now if you have to consider and so change in expansion. So this is about your entropy, that is what will the changes is occurring during the different condition. You should be remember there will be the MCQ question. Thank you.